Welcome to the fourth lecture in the fifth week of our course, Analysis of a Complex Kind. Today we'll learn about Cauchy's theorem and integral formula. Here it is, Cauchy's theorem for simply connected domains. There are lots of different versions of Cauchy's theorem. We'll be learning the one for simply connected domains. So suppose D is a simply connected domain. Let me remind you again what that means. It's a domain, so an open and connected set is in one piece, and holes are not allowed. So suppose f is an analytic function that's defined in D, and let gamma be a piecewise smooth closed curve in D. Again, here's my simply connected domain D, it doesn't have any holes, and gamma is a closed curve in D. Closed means that its initial point coincides with its endpoint. So it starts and ends at the same point. The claim is that then, if you integrate this analytic function f over the curve gamma, the integral equals 0. Let's look at an example first. Suppose f of z is the function e to the z cubed. It would be hard to evaluate an integral over gamma, no matter what gamma is, of e to the z cubed, because you can't really find an antiderivative of e to the z cubed, and the only way for us to evaluate integrals so far is to have an antiderivative, and then take the endpoint of the curve and the initial point and plug those in and take the difference. E to the z cubed is analytic in C. C, the whole complex plane, is simply connected. Therefore, we can apply Cauchy's theorem with D being the entire complex plane, and find that the integral over gamma, f of z dz is equal to 0 for any closed piecewise smooth curve in C. More generally, if you have a function that's analytic in C, any function analytic in C, the integral over any closed curve is always going to be 0. Let me quickly describe to you the idea of the proof of the Cauchy theorem for simply connected domains. This domain D that we're talking about has no holes, and therefore the curve gamma can be shrunk to a point inside D without ever leaving D. What that means is the following. Suppose this is gamma. Then imagine gamma was actually a rubber band. Then gamma, once you let go of it, would shrink. So get a little smaller, and a little smaller, until it actually collapses to a point. If you imagine the rubber band will just get smaller and smaller. So you can shrink this curve together to a point without ever leaving the domain D. If D had a hole that was sort of inside here, you couldn't do this because the rubber band would be kind of stuck around that hole. But since D doesn't have any holes, you can shrink the curve gamma to a point. And now you sort of track what happens to the integral as you slowly shrink this curve gamma to a point. And what you do is you keep track of what's happening in little disks. Here in this little disk, you keep track of a portion of the curve gamma and a portion of a smaller curve inside gamma on the way to shrinking to a point. And you realize that integrating f over this little portion that I drew in pink, that's easy to show is actually equal to 0. It uses the Cauchy theorem in a disk. And you then keep going like that. You analyze what's happening in little portions and realize that all these integrals over these little portions are equal to 0. By adding them up, you realize that the integral over the green curve ends up being the same as the integral over something like the blue curve. And then you keep shrinking the curve and end up seeing that the integral over the original curve gamma, f of c dz, is the same as the integral over just one point, the point that the curve is shrunk to, f of c dz. But once the curve is shrunk to a point, the integral over a point, the curve that's at a point, is equal to 0. So that's the basic idea of the proof. Here's a really important corollary. Suppose you have two simple closed curves. Again, simple means that a curve doesn't intersect itself, so it's not allowed for the curve to do something like this, and then continue on, so no self-intersections are allowed. Closed means the curve forms a loop, so it starts and ends at the same point. And suppose gamma 2 is inside gamma 1. So that means while gamma 1 sort of bounds a region, because it's a closed curve, and inside that region is where I find the curve gamma 2. So that's what that means. We're also assuming that the curves are both oriented in the same way, so counterclockwise, as I drew in this picture. If f is a function that is analytic in a domain D that contains both curves as well as the region between them, so the region between these two curves is this region right there, but we need D to be a little bigger so that it contains both curves as well. So maybe it's out here. It could be just a region like this, or there could be a hole in D. We wouldn't really care if D has a hole inside here because D would now still contain both curves gamma and the region in between them. So if that's the case, and f is analytic in a domain that contains both curves and the region between them, then the integral over gamma 1 is the same as the integral over gamma 2. Let me show you the idea of the proof of this theorem. It's actually just a neat trick. What you do is you make these two separate curves into one joint curve by connecting them. You pick a point where you connect those two curves and then pull them apart a tiny little bit. So you get rid of a portion of the curve that used to be here. You just erase that, but you make that so short and shorter and shorter, so in the limit, it doesn't really matter. You then form this one joint curve, which is now a simple closed curve. We're thereby able to modify the domain D a little bit so that it is now simply connected. So this domain D now no longer has the hole that we originally had. So the original domain had the hole D. We don't care about that anymore because we're circumventing that hole. So now the curve gamma is a curve that's contained in the simply connected region, which f is analytic, and we can apply the Cauchy theorem to show that the integral over gamma f of c dz is equal to 0. Let's look at an example. Suppose R is a rectangle, like the one I drew down here, the green rectangle you see down here. Centered at point z0. Z0 is simply the point where the two diagonals intersect. The claim is the integral over the boundary of that rectangle, again we assume it's oriented in the positive sense, of 1 over z minus z0 dz is equal to 2 pi I. And that is actually not easy to calculate. If you wanted to calculate this integral, you'd have to find a parametrization of these boundaries, and then finding all these integrals wouldn't be all that easy. But we can use the Cauchy theorem to make our lives much easier. In fact, what we do is, instead of calculating the integral over the green curve, we calculate the integral over the circle centered at z0 that passes through the four corners of the rectangle. So I call that radius necessary to do so r. Now, if we integrate over the circle of radius r, the function 1 over z minus z0, it's pretty easy to see that you get 2 pi I because you can find a parametrization of that curve. The curve will then be parameterized, I call this gamma. Gamma of t could be parameterized as z0 plus r e to the it. Then if you look at this integrand 1 over z minus z0, once you plug in the parametrization, that becomes 1 over z0 plus r e to the it minus z0. The z0 cancels out, so the integrand becomes 1 over r e to the it. So the integral then becomes the integral from 0 to 2 pi of 1 over r e to the it times the derivative of gamma prime of t, which is r I e to the it dt. The r's cancel out, the e to the it's cancel out, and so all you're left with is I times the integral from 0 to 2 pi dt, and that equals 2 pi I. So the integral over the circle is quite easy to evaluate and equals 2 pi I. But now f is analytic between the two curves. So the function f is the function 1 over z minus z0. It's not analytic in the whole complex plane because you can't plug in z0 for z. However, if I choose a region D, something like this, so I'm excluding this portion from D, but in this region out here, it contains both curves and the region between the curves, which is this, 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 and this. Therefore, by Cauchy's theorem, the integral over the circle is equal to the integral over the boundary of the rectangle. Let's look at another example. What's the integral over the circle of radius 1 of 1 over z squared plus 2z dz? Well, first we notice that I can actually pull this integrand apart a little bit. 1 over z squared plus 2z, let's factor the denominator, is 1 over z times z plus 2. And now you have partial fraction decomposition. You could do it the formal way, or you could see that the numerator, the 1 here, could be written as z plus 2 minus z, and you have to divide by 2 to make that true. By writing the numerator in this way, we can actually then split it apart along this negative sign, so that we end up with 1/2 times z plus 2 over z times z plus 2, which is 1 over z, minus 1/2 times z over z times z plus 2, which is 1 over z plus 2, and I pull the 1/2 outside of the parentheses. Now, therefore, I can also pull the integral apart. The integral of 1 over z squared plus 2z becomes the integral of 1 over z minus the integral of 1 over z plus 2, and the 1/2 again is in front of here. But the integral over the circle of radius 1 of 1 over z dz, we calculated that. That integral equals 2 pi I. Whereas the second integral here, we're integrating over the circle of radius 1, which I'm drawing right here, the function 1 over z plus 2. Where is that function analytic? Well, it's analytic everywhere except when we divide by 0. When do we divide by 0? When z is equal to negative 2. So z equals to negative 2 is a point at which the function is not analytic. Everywhere else it is analytic. In particular, this function 1 over z plus 2 is analytic, for example, in the circle of radius 1.5, centered at the origin. In that circle is contained the curve gamma over which we're integrating. So the function is analytic in this big disk. It contains the curve over which we're integrating, and therefore the integral, the second integral right here, is equal to 0 by Cauchy's theorem. Cauchy's theorem implies a very powerful formula for the evaluation of integrals. It's called the Cauchy integral formula. Again, there are many different versions, and we'll discuss in this course the one for simply connected domains. So again, let D be a simply connected domain bounded by a piecewise smooth curve gamma. So gamma here is this red border of the domain D. And let F be analytic in a set U that contains D and the curve gamma. So U is a little bit bigger, so that it contains not only the domain D, but also its boundary. The claim is then the integral of f of z over z minus w over the curve gamma times 1 over 2 pi I is equal to f of w for any w inside D. You can recover the value of f at any point w in the domain D by integrating f of z over z minus w along the boundary curve gamma. The boundary curve gamma therefore contains all of the information about the function in the inside. This is quite remarkable, because on this integral you're only evaluating f of z for z values from the curve gamma, yet you're able to recover a value of f inside the curve D. Before we look at some examples, let's quickly look at how the proof of the Cauchy integral formula goes. Here again is this curve gamma that bounds the domain D, and then U is something bigger around here. So U is this set that contains D and the curve gamma, in which F is analytic. We now pick a point W inside D, and we know that because it's inside D and D is open, we can find a little disk of radius epsilon centered at W that fits entirely into D. Now, we can use Cauchy's theorem and observe that the integral over the curve gamma of f of z over z minus w is the same as the integral over the blue curve of f of z over z minus w, because the function f of z over z minus w is analytic between the two curves, on the curves, and even a little region that contains both curves. We just have to avoid the point W. Now, again, the integral over the blue curve is pretty easy to evaluate. The integral over the blue curve is the integral over the boundary of this disk of radius epsilon centered at W, f of z divided by z minus w. The way you evaluate that, you plug in a parameterization. The parameterization is gamma of t is equal to w plus epsilon e to the it. You plug that in and find the integral of f of gamma of t divided by gamma of t minus w times gamma prime of t dt. And a lot of things cancel out just like I did in the example before, and you end up with the integral of f of w plus epsilon e to the it. This is true no matter how small you choose this value of epsilon. Epsilon was the radius of the disk centered at W that fits into D. It didn't matter how small that was. As you let epsilon go to 0, the integrand more and more looks just like f of w, which is a constant. If you integrate the constant f of w from 0 to 2 pi, you get 2 pi times f of w, but we're also dividing by 2 pi, so that this integral in the end becomes f of w. And that's what we wanted to show. So the proof of the Cauchy integral formula really essentially uses the Cauchy theorem and the conclusions we had drawn from the Cauchy theorem. Now let's look at some examples. Here again, I just reminded you of what the Cauchy integral formula looks like. It says that the integral over the closed curve gamma, which is the boundary of the region D, of f of z over z minus w dc times 1 over 2 pi I is equal to f of w. So here's the first example. Suppose we wanted to find the integral over the circle of radius 2 of z squared divided by z minus 1. So here's our situation. We have the circle of radius 2, oriented counterclockwise as always, and the function z squared divided by z minus 1. So let's match things up with this formula. Z squared, that's our f of z. W, that's this one right here. We need W to be inside D. D is the disk of radius 2, but W is equal to 1, and indeed that's inside D, my disk of radius 2. So we can apply this formula, and it tells us that 1 over 2 pi I, the integral over circle z equals 2, f of z over z minus 1 dz, is f of W. W is 1, so that's f of 1. What is f of 1? We plug in 1 for z, that's 1 squared, so that's 1. So the Cauchy integral formula says that 1 over 2 pi I times the integral we're interested in equals 1. Therefore, the integral that we're interested in, we can find that by multiplying 2 pi I, and we find the integral is equal to 2 pi I. Let's change things up a little bit. This integral looks very similar to the previous example at first sight, except that we have w equal to 2, and this time we're integrating over a circle of radius 1. Let's start a quick picture. So we have a circle of radius 1 for our curve, and again we have f of z is equal to z squared. And so at first sight, you would think, well, f of z is z squared, w is equal to 2. However, where is w in my picture? 2 is out here. It's not inside my region D. And therefore, I cannot apply Cauchy's integral formula because the w's that this is valid for have to be inside D. So what is this integral z squared divided by z minus 2? Well, this function z squared over z minus 2 is analytic in the disk of radius 1.5 center at the origin, which contains the curve gamma. We can therefore simply apply Cauchy's theorem. We don't need the integral formula. The theorem says that the integral over a closed curve is equal to 0. Let's look at another example. The integral over the circle of radius 1 of logarithm of z plus e divided by z. Remember the logarithm function? The logarithm of z was the natural log of the absolute value of z plus I times uppercase argument of z. And my z's were allowed to be in the entire complex plane except the negative real axis. This function is analytic in the plane minus the negative real axis. Here we're looking at the logarithm of z plus e, which is shifting the region in which this function is analytic. The logarithm function was analytic in the plane minus the negative real axis, but if I add e to every single one of my z's, I actually make a function analytic in the complex plane minus the portion of the negative real axis that ends at minus e. Because anything that's bigger than minus e, once I add e to it, ends up in the right half plane where the function is analytic. So this numerator here, my function f of z, is analytic in the complex plane minus the portion of the negative real axis that ends at minus e. W is equal to 0. I'm going to see a minus 0 right there. F is analytic in the whole plane minus the portion of the negative real axis ending at minus e. In particular, it's analytic in this region right here. That contains the curve we're integrating over. We're integrating over the circle of radius 1. W is inside that curve. W is equal to 0. And therefore, the Cauchy integral formula tells us that the integral of logarithm of z plus e over z, which is exactly this integrand except for the 1 over 2 pi I in front of it, must be 2 pi I times f of w. So that's 2 pi I times the logarithm of 0 plus e. We're plugging in 0 for z. But the logarithm of e is the natural logarithm of the absolute value of e plus I times the argument of e. The e is a positive number, so the absolute value of e is e. The natural logarithm of e is simply 1. The argument of e, on the other hand, e is a positive real number. The argument is 0, so that's 1 plus I times 0. So that's simply 1. Multiply that by 2 pi I, the outcome is 2 pi I. Here's an amazing consequence of the Cauchy integral formula. It's the following theorem. If f is analytic in an open set, then f prime, the derivative, is also analytic. And therefore, f prime is an analytic function whose derivative you can find. So you can therefore find the derivative of the derivative. So the second derivative exists. But then by the same theorem, the second derivative is also an analytic function. So you can find its derivative. And moreover, its derivative is also, again, an analytic function. So you can keep finding derivatives and you never have to stop. So once you have a first derivative, you have all derivatives for this function. We'll denote derivatives like that by f and then put in parentheses the number of derivatives we're actually taking. Here's the idea of the proof. We first use the Cauchy integral formula to show that the derivative f prime of w can be found using this formula. Here's how you would do that. So by the Cauchy integral formula, we have f of w itself is 1 over 2 pi I times the integral over gamma of f of z divided by z minus w dz, where gamma is simply the boundary of a very small disk centered at w. So here's your w inside this region u where f is analytic, and you simply choose a little disk centered at w so that the entire disk is contained in u, and its boundary is your curve gamma. So the Cauchy integral formula then tells us that f of w can be found by integrating f of z over z minus w over this curve gamma. And then you ask yourself, what does the derivative look like? So you could look at the difference quotient f of w plus h minus f of w over h, and you simplify that and show that in the limit, this is what you get for the derivative. Next, you look just at this function right here on the right, and you show that it actually forms an analytic function. So you forget that that actually equals f prime of w, and simply show that a function of this type is analytic in w. So it varies as w varies, obviously, but it varies in analytic fashion. Therefore, f prime must be an analytic function. So repeated application of the previous theorem shows that an analytic function has infinitely many derivatives. Continuing along the same lines as in the previous proof, you can now find extensions of the Cauchy integral formula about derivatives. If D is a simply connected domain, as before, bounded by a piecewise smooth curve gamma, and f is analytic in the set U that contains the closure of D and gamma, so same setup as before for the Cauchy integral formula, then not only can you find f of w, but you can find all of its derivatives via very similar formulas. So again, the setup is you have a set U, and then you have this region D inside it that is bounded by this curve gamma. And for any w inside gamma, you find the kth derivative of f at w can be found by taking k factorial, that's k times k minus 1 times k minus 2, and so forth, all the way down to 1, divided by 2 pi I, times the integral over the boundary gamma of f of z divided by z minus w to the k plus 1 dz. So the only difference to the previous formula is this k factorial here. There used to be a 1 there. And this k plus 1, which also used to be a 1. So we have the case when k is equal to 0, 0 factorial by definition is 1, and then 0 plus 1 is also equal to 1. So again, fk denotes the kth derivative. So not only can we find the values of f at w by simply integrating f of z divided by z minus w to some power over the curve gamma, but we even can find all the derivatives as well. So by only knowing f along this curve gamma, we can find information about f and all of its derivatives inside gamma. That is quite amazing. Let's look at another example. Again, here I wrote down the formula for the derivatives, and now let's try to find the integral over the circle z is equal to 2 pi and absolute value of the function z squared sine z over z minus pi cubed dz. Let's match things up again. First of all, this z squared sine z, that seems to be our f of z. W is pi. And then k plus 1 is 3, which means k is equal to 2. We therefore need to find the second derivative, f2 of pi, in order to evaluate this integral. And then we need to multiply that by 2 pi I and divide by k factorial because we want this integral by itself. So we need to find the second derivative of this function z squared sine z. Well, the first derivative by the product rule is 2z sine z. We just differentiated the z squared portion, plus z squared times cosine z. Now we differentiate sine z. And the second derivative can be found similarly. Here it is. And when you plug in pi into the second derivative, this term cancels out because sine of pi is 0. This term cancels out because sine of pi is 0. You're left with 4 pi cosine of pi. Cosine of pi is negative 1, so you get minus 4 pi for the second derivative of f at pi. Therefore, this integral that we're interested in is, we're bringing this 2 pi I to that side and also the k factorial, is 2 pi I over 2 factorial times the second derivative of f at pi. 2 factorial is simply 2 times 1, so that's 2. And we have 2 pi I times minus 4 pi divided by 2, which simplifies to minus 4 pi squared I. So this integral equals minus 4 pi squared I. Here's another example. Again, this is the Cauchy integral formula for derivatives. And now we want to find the integral over the circle of radius 2, e to the z over z plus 1 squared dz. Set up, we're integrating over the circle of radius 2. That circle contains negative 1, which is our w. We have e to the z being the function f of z, and we have k plus 1 is equal to 2, so k is equal to 1, and we have w is minus 1 because we have a plus 1, which is minus 1. Therefore, we need to find f prime of w, so f prime of negative 1. F is the function e to the z, its derivative itself is e to the z, so f prime of negative 1 is e to the negative 1, which equals 1 over e. Therefore, the integral of e to the z over z plus 1 squared dz, again we bring the 2 pi I and the k factorial over to the other side, is equal to 2 pi I over 1 factorial, f prime of minus 1. 1 factorial is simply 1, so we find 2 pi I times f prime of 1, which was 1 over e, so 2 pi I over e. That's kind of a fun result, because 2 pi I over e contains 4 of the most important mathematical constants. 2 is the only even prime number, pi I e, that's kind of a fun result. Okay, enough for today. Next up are some amazing consequences of Cauchy's theorem and integral formula. We'll see the maximum principle, Liouville's theorem, we'll be able to prove the fundamental theorem of algebra, so we'll have lots of fun in the next lecture.